reflection problem. I think there's one in there. Chapter 4. That's chapter 2. Any more weird ones? Well, I don't have many more. I think I had this one, did this one in class. Wish I had. Excuse me, that's gross. I want to be able to do one in FEA and compare it. It's danger here, though. So let me make up one. All right. That's dangerous. Making up one. Danger's my middle name. It's not true. James. So, what's it? It's Friday the 13th, isn't it? Yeah. Gotta make a little hockey mask. I'm getting a little angry. ME370. Friday. Week 5? 6. Let's go with 6. I'll do slightly different. Let's make the thing come up and over and connected, and let's make the force come up here, that direction. And let's make this 12 inches. It's not the same as I did in the homework, is it? Did I get 12 inches? I could make it metric instead. You're not answering my questions. It's because you don't like me. Is that why?
You're focused on drawing the diagram.
Okay. 10 inches. 8 inches. This is not the same as ours. Ours actually has a force coming out in that direction right there. So this has some quirks that yours doesn't. It has a quirk, at least one big quirk that yours doesn't. And let's say that this thing is going to be proportional. Let's make it 1.25 inches in diameter everywhere. So pi over 4, 1.25 inches squared, pi over 64, 1.25 inches fourthed, and J is pi, just go 2I. Kaboom! 1.25 squared. I don't need to do that. Pi times 4 divided. So we get 1.2272. Well, no, but we don't need. And then 1.25 enter 4 pi times 64 divided. That doesn't seem right. There, all right. 1198. have a find. That would be good out there. Find delta y. Okay? Makes sense? The same direction as this f. And let's decide that that f, we'll call it fy. Fy. What do you think a reasonable size? Can you picture this thing? It's about 12 inches long. Let's just say, let's say we want to get a good solid number out of it. Want to go 500 pounds? Seems like a lot.
Strong material though?
Yeah. Maybe not so much, because we want to do an FEA of it, and we don't want it to go into a crazy nonlinear mode because we want to, so 200 pounds. Well, 200 pounds. That's pretty, yeah, just made them, okay. And we're picking steel. Interesting what aluminum would do, but. So steel, we're gonna try that. So we're gonna say E is equal to 30 E6 psi. So maybe I'll just march through this, and I'm gonna call this A, B, C, D. And so my first one I think I'm gonna do is bending of CD. So I'm going to go from that direction through the thing. So the deformation of D, and we're trying to find, by the way, we're trying to find del dy at D. It's more specific. Not a very good looking subscript there. So we go the deformation of D, I guess due to F, yeah, due to Fy. So we look that up. So that's just going to be, by the way, sometimes I like to draw this out. So this is going to be sort of, it's not a free body diagram, it's just a diagram I'm using for myself to try to think my way through this. So it's going to go like that right there. Right? So we're going to have this deformation right there. And that's going to be, so we're treating this like a cantilever beam. And we could parse the idea that, like, well, maybe we don't want to go the entire 8-inch length. Maybe we're going to go 8 inch minus 1/2 of 1.25. You see what I mean? We might want to do that, but let's just go ahead. Let's go ahead and let that be an error. Right? We're just going to treat it like it's cantilevered right here instead. So we'll use that 8-inch, full 8-inch. So we look up and find what case number this is going to be for bending, and basically for our homework, we're going to be doing pretty much the same one everywhere, and that's going to be case number 1, cantilevered, and it's a maximum cantilever thing of F L cubed over 3EI. So F L cubed, and I'm not bothering with the minus sign, 3EI. And if we're going to say the L here, we can make it specific. We can make that to Y right there. We're going to see the LCD. So we're going to take a 200 times the 8 cubed divided by 3 30E6, and then the I was 0.1198 if I did it correct. I have suspicions. So 8 cubed, 200 times 3 divided 3, E6 divided, and 0.1198 divided. and we get 9.497 E minus 3, and these are inches. All right, so next victim. I'm going to go BC, and that's going to have some axial deflection. Now, by the way, the axial is usually a lot smaller than all the other ones right here. So we're going to go axial of BC. So it's going to go up right there. All right, so because this force is over here, we can just try to kind of move him over to here and see that this guy is going to be an axial because he's in line with the Fy. So it's going to have that amount of deflection. I didn't draw it very well. Del of C, I guess due to Fy, sure. So that's going to be, we found this, I could try to memorize it, right? There you go. All right, so the deformation due to axial is going to be equation 4.3 FL over AE. Notice how similar it is in this form to the other. They have the same kind of form. So the L is going to be BC. That's the one that's right there. And of course, this is still Y. So we have 200 L10 A 1.227 E30 E6. 210 1.227 30 E6. Well, yeah, so it's 2 orders of magnitude. Well, 100 less. Trying to think, words aren't working for me right now. E to the 3 versus E to the 5. E to the negative 3 versus E to the negative 5. Didn't expect much. Here's one that's a complicated one that you probably wouldn't know. Here's one you wouldn't expect. It's like a 2-stepper. But if you look at this little segment right here creates a moment onto this beam. And that moment is going to make this part go up. Right? So what you need to do is you need to find the angle of this piece. Let me draw this right here. So this is the bend due to the bending of CD. And what that's going to do, let's see if I can put this thing up here. Let me do it in 2 stages. That's going to create a moment, M, which is going to create, it's hard to draw this and get all the information I want onto here. It's going to move up like this right here. And that's because of this moment. And that's going to create an angle. Right? And that angle is going to be the same angle as this. Which creates this deflection. You don't have this in your homework. This is not a feature of your homework, but this is just a, hey, we ought to recognize and try to visualize all the things that could happen. I didn't put it into this one. I had put this into the homework before. It's all if I had made the force in the vertical direction, it would have been there. But this is a demonstration of thinking through a problem. So the moment, without doing a free body diagram, because that would have been the right thing to do, is just going to be Fy. Well, I can just put the numbers in. It's going to be 200 times 8. Right, so like looking back up at the top, this guy right here, holding right here, he creates a moment about that spot of 1,600 inch-pounds. And now, and we don't care about the distance that this would move right here, but we could find it out. But instead, what we need is this guy. Boom. We get the maximum. But we need the angle, not this. How do we get the angle? Right, so we want the angle here at the end. We could just take the derivative of this with respect to x. Right? Because that's going to be the slope. Anytime you take the derivative, right? So this right here is the maximum. Of course, it has L. But here is the shape. Here's the deformation at any given point along the x. And we want to find the deformation, the slope, right there. So that's the dy dx. We'll give them some radians, but that's totally fine by us. Radians is what we want, because we're going to multiply that angle times the length of the thing and then find out how much it moved. So let's memorize y equals mb x squared 2ei. I don't need to memorize it. Just look over here. So y is equal to mx squared over 2ei. Therefore, theta, which is dy dx, is equal to 2mx over 2ei. Or just m. And then here's it at L, at x equals L, the 2ml, or ml over ei. And that should give us radians. So 1,600 times the length right here. This length is going to be the length of BC, right? Because that's this length right here that we're putting a moment onto the end of. So that's going to be the 10. And then the E, 30E6. And the I is 0.1198. So 1,600, 10, 30E6 divided, 0.1198 divided, and 4.4519 E minus 3, but these are radians. Now, if we're going to get the deflection, and I'll say this is deflection at D due to M. I just got to give it a name. I don't know how to, the right way necessarily to do that. And so what we're going to do is we're going to take LCD times theta. Right? Because that's going to be this right here. Here's the theta that is moved. Because you could think of it as having rotated. So 8 times 4. I don't know what I was thinking. 4.4519 E minus 3 Just multiply by 8. Boom. So this is a big deflection compared to the others. And if you left it out, it'd probably be a big source of error for us. So you see that it's a good size e to the minus 2 compared to e to the minus 3, and the minuscule e to the minus 5 with that one. Let's see. Anything else on there? All right. I think the next one we want to try to do is going to be the bending of AB. All right. So this is going upwards, which is going to make this bend that way, upwards, which is going to move C, which is going to move D. We're okay with that? Bending of AB. And so I'm going to look from the side over here. You can't quite see that part right there. He's coming up, but he's going to bend up that way. All right, so we're going to go up that direction. I put this too close to my title right up in there. So that's going to be the same equation as this one up here. It's the same cantilever type of behavior. So the here's the del, and this is going to be the B due to F. So FY, L, and this is going to be AB is the length, and 3EI. No, 3EI. So 200, LAB is 12, 330E6, and 0.1198. 200, 12 times 3 divided 30E6 divided 0.1198 divided. Pretty good amount. 2.226 E minus 4 inches. All right, this last one takes a little bit of explanation as well. There's quite a bit of thinking here. Try to see if we can do this right. Yeah. The last one, I think, unless I miss one, which is totally possible, we're going to have the torsion of AB. So let's see, well, how is that going to happen? Okay, so this torsion arm is going to create a moment here, which is also going to translate down to here and twist this piece. All right. So it's still going to be it's the same moment that we had at the top of this is also going to be all the way down to this thing. So this is going to twist. It's going to make this go that way, which is going to lift this up. Right. So it's a little bit of here you go. That's right here. Onto the thing right here. I gotta plan out my little sketches a little bit better and leave myself some room. All right, so we're putting a torsion onto here, and it's going to make this angle change, and that angle change is going to be the same angle change as this right here, which is going to cause this amount of deflection. So it's going to be del, I guess it's still going to be D, but now it's going to be due to T. So this is going to be the angle change of AB, TL over JG is what I have memorized. But if you wanted to double check, because I don't know, I wouldn't take my word for it. And I'm me. Pretty sure. There you go. TL over GJ. JG just runs off the tongue. Slip off the tongue. It's better than GJ. I'm JG now. I don't know. Maybe because I was once a Lieutenant JG. Junior grade. Lieutenant JG. They promoted me to Lieutenant Commander. It's kind of weird. Lieutenant Commander. I like the JG bit. Okay, so we're gonna need G. We can look that up. We could probably calculate it ourselves with the Song's ratio, but for carbon steel we used 30, so we might as well be consistent here and have our modulus of rigidity to be 11.5. I love that name, modulus of rigidity. I want to name my band that. It's better than circle of Willis. Anything's better than circle of Willis. So I didn't write that down. I can't remember now. 11.2? What did I say? 11.2? 11.5. That is some serious short-term memory right there. Serious short-term memory issues. Okay. So, and this L is, okay, so the torque is going to be equal to 1,600 inch-pounds. It's that same amount, because it's the same CD thing that's creating this, right? We were thinking, well, what's the torque? Well, it's going to be the force times the distance perpendicular to it to the point about which we're doing, which is still going to be 8 inches. So it's still the same thing. And the length is going to be AB. So we're going to go 1,600. I don't know what the hell that was. Sort of a comma. The length is going to be 12. The J is going to be 0.2397, and the G 11.5 E6. Have I done the Holy Hand Grenade of Antioch? Are you familiar with the Holy Hand Grenade of Antioch? From Monty Python? Yeah. Where it goes 1, 2, 5, 3, 3. So you have to screw the thing up. 3, 3. Old calculator here. The Holy Hand Grenade of Antioch.
What they use against the beaver?
I think no, it was against a rabbit.
Rabbit, yeah.
Look at the fangs. Look at the bones. Look at the bones. You made me so in my armor.
You right. They actually didn't finish the end of that movie because they ran out of budget, right?
Is that why they had the odd scene at the end at the French castle?
Yeah.
Go away, or I've told you a second time. I blew my nose at you. Alright, so here is the angle that changed, and now we want the deformation. We're going to use the length of CD. We already walked through the logic of that. That kind of always bothers me, because I almost kind of want to use the length of this guy, but he doesn't really matter. Although, to tell you the truth, this actually gets a little bit shorter. We could actually the top of this is actually dipping down a little bit because of this angle. Like, C is actually getting lower. An itty bitty tiny, we can explore how much is C dropping vertically down because of BC's rotation. We could look at that. We're like neglecting it right now because we're just going to take this angle and multiply it by this because we want to see how much it raises. So we're going to say that's LCD times theta AB. So, numbers, 4.002. Knee bent, walking around and such. Good away, I'll also told you the second time. Your mother was a hamster, and your father smelled of elderberries. You have no idea what I'm talking about, dude. What's that? That's from the ending of Mike Python. Yeah, the Holy Grail. The French taunting. No, that's not the end. It's earlier. The French dude comes back at the end of the castle, where the Holy Grail was supposed to be. All right, so I think we have all of it. Let me do this little check. We're going to check how much does C go down due to theta AB. Well, let's see, this is the angle right here, that theta, and so it would be this amount right here. Right, because he kind of goes down that way right there. Del C is going to be equal to, we'll treat this like the hypotenuse, which is true. Well, thing is, this is an approximation too, because you could say that this is the hypotenuse. You could say that this is not a square right there. You could say that's not a square angle. Let's pretend like it is a square angle. Really what you're checking is LBC minus LBC cosine. Is that right? Yeah, it's going to be close enough. Cosine. So theta AB. Close enough. I just want to see how small it's going to be. It's going to be really small. Spoiler alert, really small. 4.002 E to the 4 minus, what we're going to take, wait, I got to turn that into an angle. We're going to have to shift into radians. I don't like doing radians. I'll do it anyway. I'll shift. I'm just going to hit enter. Hit enter and then go to mode and go to 2. I don't like going into radians because I keep forgetting all the time. So we go cosine, basically 1. Yeah, it's so small, it's basically 1. So it's even up here to 5, 6 figs, it just turned into 1. So that's how small it is. So we can multiply it though. I can multiply that by 10 inches. And then subtract it from 10 inches. And it ends up being 8.008 e to the minus 7. So very, very small. I'm going to turn my thing back into degrees before I forget. Because I've gone like halfway through a problem in all kinds of classes where I had it in radians. I'm like, what the hell is going on? It's like, oh, calculator in radians. It's a classic. Okay, so let's find the deflection in y by taking all of these parts. Let's see. We had a deflection of d due to Fy. And this is the principle of superposition. D due to moment plus B due to F. And then the last one was plus D due to T. And you can see that this already, we don't even need to deal with this one because we're, even the axial was e to the negative 5, and this one is like way the heck out of there. So, let's go 9.497 e minus 3 plus, and this is the axial right here, right? 5.433 E minus 5 plus, where'd you go, 3.562 E minus 2, that was a big one, plus 2.226 E minus 4, and then lastly 3.202 E minus 3. I don't know why that parentheses decided to jump out of it. Calculator fodder here. So 9.497 E 3, boom, 5.433 E5 plus 3.562 E2 minus plus 2.226 E4 plus, and then 3.202 E3 minus plus. Boom. We get a total of 4.8596, so 60. E minus 2 inches. But let's check it, because we can.
What's your favorite waffle place on the movie?
I'd probably Holy Grail. I do enjoy the Life of Brian. I think I saw it. How come you're not opening that? Oh, your install is incomplete. What? Alright. It's trying to open it up twice now because I was just so very. Look at it, open up 3 times. Mr. Impatience. This laptop's 2 stories at once. Not put the stories already yet. My roommate in college, Andy, would be so very impatient that he would break. He literally he'd like tap on his keyboard and then hit the backspace. Like he hit the keyboard so hard, he's so impatient. First off, he would lock up the computer like all the time because he just was so impatient of it. But when he actually broke a couple keyboards, you know how hard you have to hit to break keyboards. Great start there. Let's see how we're gonna make this thing. I'm gonna make a 3D sketch. And boom. And so I'm going to go up, boom, go in that direction, boom. I just made that look like way easier than it is. See, I lied. Okay, so I think I need this to tell this is going to be in the Y direction. So let me do it. Yeah. I think I need to tell him he's in the X direction. I hate you people. Why won't you do that? I think he's already in the Y direction. And then he needs to be in the Z direction. I don't know. I think I have whatever it is right now, the relations turned off. I think there's an automatic relation in that. Let me take a look at it. Yeah, it looks right. Okay. So let's see. Whoop, I did it wrong. Why did I do it wrong? Let me start over. Sorry. One more time. Need to be in the X direction. Need to go up and be in the Y direction. And then I need to be in the Z direction.
Hit tab.
What's that?
Hit tab.
Hit tab?
Yeah. That's usually how you cycle the directions.
Oh. Yeah. All right, what is that? to go crazy. That's actually going to make it. Actually, the filters are going to give us a little bit of error. It's going to be a source of error for the thing. But it's not going to get. I guess I'm just being lazy if I put the fillets in there. I'll go. No, let's go 1.3. I think that'll work out best. It is a source of error though. And then we're done. And then here on the right plane, make a sketch down here and make that 1.25. And then sweep. What's that? Yay. And so make a simulation. Where'd you go, simulation? It disappeared. Is that because I effed up and when I opened the thing up?
Probably not.
What are you doing? It was not there. Simulation disappeared. Add it. Simulation. It's because I tried to open up too many things all at once. It disappeared. Go to a new study, static study. Yes. Right here. You'll apply material. This will have the biggest effect right there. This one has a pretty close to 30 million elastic modulus. That's the most important one. The sound ratio might, not really. But you could go through here and start looking for it. Here's like 29 million. You really want, if you want your numbers to match up, or apples to apples kind of thing going on here. You want to try to find one that's like exactly 30 million. I guess that alloy that we started out with, that's probably the best one I saw so far. Right? There's no difference there. It's A36 actually has a 29 million. Yeah. I guess let's just stick with the alloy steel, knowing that that's going to be one of the biggest contributors to a difference, because that is what the stiffness of the material is. We have fixtures and we can fix. Go to external loads, make it force. Have it right there, except we need to select the direction. Go away. And English is, let's see, is it going to go that way? Nope, they go the other way. Boom. And make it 200. No, 200. I don't know why it does it all the time. 200. I think I can click over someplace else. Yeah. I couldn't hit enter. I don't know why. That's a weird quirk. I think that's good. All right. And, just create a rough mesh. Go with the default. Actually, I want to make it rougher than that. Let me make it rougher than that first. Create a mesh, make it coarse. Yeah, still kind of finer than I wanted to see if I could make it so that it would be a bet. We could improve the number. Let's run it. Boom. Want to see displacement show, and let's turn the definition. It's in millimeters. Let's turn it into inches. We can also, by the way, change the scale. Right now it's automatically multiplying the deformation that we're seeing by 9.88. If you put it to true scale, you'll see that you could barely see. Actually, you can see something. Let's put you can also put in the ghost of it in there. Let's see, show colors. I think it's settings. You could put superimpose the original one with a transparency if you want to. So now you can kind of see. So here is actually a true scale, so you can kind of see how much it's moved. That's interesting. that way right there. Usually though, it's going to be so small that you can't even tell. So that's true scale. Let's go to the deformed scale. You kind of see how much it's lifted up. Kind of see, you can kind of see the curvature of that, not quite the bending. The curvature of this one. You can also see it from this point of view. You can see that it's bending upwards like that. You get kind of a sense of what we've just done. Well, here's the important part is that we're going to try to find what the results are. I like to pick the entire face and then look at the average. All right, so pick up that whole face right there because it's moved because it's at an angle right there. So if you pick at the top, it's going to have a slightly different difference. So if you hit update right here, and what our average is going to be, ours is very wrong compared to theirs, huh? 1.5E1. So I missed something somewhere, or I made a numerical mistake. I usually get pretty close. So where could I have made a mistake, I wonder? Well, definitely the radius of curvature is going to have an effect, but I would have thought that it would have a stiffening effect as opposed to here where we have a larger value. Oh, wait. I know why. I made a mistake. Here you go. We're going to fix it. This is always, it's always something. The answer right here, that guy, that's the resultant. So that's going to be all of the deformation in the X, Y, and Z, the square root of the square of all those displacements. We only want the Y displacement. Boom. So when we go back up to here in the plot tools, in the list selected, go onto here and update, and how did we do? Didn't help me. Damn it. I was all excited. I still have a 0.125 or e to the 1, e to the minus 1 as opposed to like e to the minus 2. So I'm like 1/2, right? Am I about 1/2? Is that correct? About 1/2. So I wonder where the other deformations are coming from. I was all excited that the thing got wrong. I don't know. But generally speaking, I'm usually able to get pretty close. I'll have to think about it. I'll follow up at some point. Follow up. Find where I might have gone wrong. I'll put it on the internet. And of course, everyone on the internet knows more than everybody else. So someone will be able to figure out what I did wrong, what I left out. I wonder if the twist, I wonder if there's another deflection due to the twisting. I don't know. Seems to me this is making for a good video. Torsion of AB causes dizziness. That's where that pool noodle thing helps me out. I taped another pool noodle onto my already bent pool noodle, so it made kind of something similar to the shape right here, to try to think your way through the different parts. I'm having deja vu here. I've made these same mistakes before. Did you check? Were you checking my math as I was going through?
Yeah, that's right.
Okay. Well, we see the e to the minus 2, 3, and 3 to the 7. E to the 3 there. You kind of almost think that, where I suspected the most? I suspect
this to be a larger number. I expected this radians to be a larger number. The amount of angle here, I would have thought would have been way more. This is actually, yeah, this is a lot smaller than that. So let's see. Right, because this thing is twisting, and I would think it'd be really subject to being twisted. Say it again, I'm sorry. I was.
Are you talking about your data?
Yeah.
Yeah.
Yeah. Oh yeah. Big time. 6.965 E minus 3. Right, so that's going to be significant difference here. So 6.965 E minus 3 times 8. Boom. So, oh yeah, it's 5.5722 E minus 2. E minus 2. So, plug these other ones in there. By the way, this makes it a good case for things I have said before about in-between numbers and how writing them down can be very beneficial to, oops, let me do that. E4. It's hard to talk and walk. It's hard to do everything at the same time. Very beneficial to trying to troubleshoot and do sanity checks of your final answers. What caused what? And if you always keep everything in your calculator, hit equals at the end. When people do that. So I got 1.5539, it's too many sig figs, E minus 1 inch. Okay. So how do we do that compared to this? I should have written down what this was. So here, update, come on. And yeah, well now we got more than the FEA, which kind of like, that makes a little bit more sense because we're having these fillet radii, 1.253. Or 0.253. So a couple of things we might want to do is remesh it. Well, actually, in our model, those fillet radius look like way more than I intended them to be. So I can go to here, and I think it will let me. Will it let me? It's not letting me. Can't I just? Oh, there it is. Okay. What if I go down to 0.5? Will it allow it to be built? No. I might want to undo and then change.
475.
And you do the negative,
Okay, it's very generic. Yeah, I could barely do it, but I can do it. Alright. So, mesh and run. So let's see, what would the effects of this be? We're going to go to displacement and plot tools. List selected. Boom. Update. Didn't help too much. We'll tell you that. One thing that could have an effect, but maybe not. Create mesh. Yeah, sure. Grab over this all the way across. So, yeah, that's not actually doesn't look all that fine. So you can look, was there control? I can't remember. No, it was fine. Run. And I don't know if it'll have any effect at all. Come on, Kara. Plot tools. The brain is just not working. No, just same 1.7 versus 1.55. Huh. I do think that the stiffening, the assumption that we're coming right from the center onto the thing, probably would have gotten less if we had taken account of the width of the part. But we're in the ballpark. That's good. I like it. When you're plotting these things, I'm breaking my own rules here. I usually like to have a breakdown. Let's see. We're going to 0.12. So let's just take this from 0 because we don't really care about it coming from there. The negative deformation. Might want to make this one 0.125. And 0.125 can be divided by. Can it be divided by 12? No, so instead, maybe I want to make this 0.12. Yeah, 0.12. And then make this 12. That will give us even increments. And also, if we're going to make a fringe plot, I think making discrete looks way better. Boom. Oh, and scientific notation, where even though I use it a lot, I think it looks better when you're presenting something. I think just your audience would appreciate having like floating values, and I guess that's fine. 3 sig figs is probably okay. One of the quirks of SolidWorks simulation there is that like when you go to grab a number off of that plot tool setting that I was using, it uses the same number of decimal places as you choose for this right there, which is, we would rather have at least 3 decimal places for something like this, which is all, just to have enough sig figs. But yeah, so plot scales I really think are important on legends to communicate effectively. And I was just talking with one of the guys in FSAE, for some of the parts that he's doing stuff on, and telling him, one really important principle I really adhere to is if you're going to do a document where you have multiple prints of the same part, you're explaining where you change the loads or you're changing other things. When you need to be comparing, always use the same legend. And I've seen that before, where you just can't make heads or tails out of something if the legend changes every time that you plot the thing. And that's what's going to happen if you just accept the default legend. So, if nothing else, pick a legend and stick with it throughout a particular report. So anyway, I think that's enough for today. Does that help? The kind of consolidation of some of the stuff. But also I think it was important to see, hey, I got something that didn't make sense on the piece of paper, didn't match with the FEA, and then I tried to resolve it. I got to tell you how important that is. That's why you do the thing on the paper to check the FEA, and that's why the FEA is a good tool to use hand in hand with doing hand calculations. It can't replace it, not 100%. But you can get insight into, by hand, what caused each of these deformations that you can't get with the FEA. So say that you wanted to change, you wanted to redesign this, so to minimize its deflection, you know the causation of that, the major drivers, and you could change it accordingly. Maybe make one of the diameters bigger than the other, whatever. All right, let's